Everybody for coming. All right. Thanks everyone for coming. Today we have with us Zufen Wang, who is a student, a PhD student here in our department. And she does research on, as far as I understand, on control strategies for HVAC systems. And I think that's what she's gonna be telling us about it today. And she is close to graduation, so I'm sure she appreciates any feedback that we may give her after her talk. All right, so Zufen, thank you for giving the talk, and the floor is yours.
Thank you for the introduction. Good morning, everyone. My name is Zufen Wang, a PhD student in department, EC department. My topic today is about the evaluation of nonlinear control performance of air handling units under variable operation conditions using root distribution approach. Here is the outline. First, I will give them introduction, then the objectives, and then I will introduce the conventional root lockers. Based on this, operation parameter-based root distribution will be extended from the traditional root lockers, and we will use the root distribution to evaluate the nonlinear control performance at air handling units. And finally, I will give the conclusion. HVAC systems account for 50% of the energy in commercial buildings, and up to 25% to 77% energy waste can be created by improper control design and operation. There to maintain the indoor thermal comfort and the indoor air quality, there are 3 control systems at air handling unit. One, the outdoor air damper control system, the supply fan speed control system, and the cooling coil valve control system. And for my research, I will mainly focus on the last 2 control systems. And for the fan speed control system, the fan speed is modulated to maintain the duct static pressure. For the valve control system, the valve position is modulated to maintain the supply air temperature. Generally, the 2 control systems are designed as a single loop feedback control systems. And for a single loop feedback control system, there are 3 components in addition to a controller: the actuator, the plant, and the sensor. If assume the system is linear systems, then each component can be modeled as a first-order system with fixed gain and time constant. And the controller is designed as a PI controller with fixed gains. In practice, due to the weather and the schedule change, we have variable space cooling load. And because of the variable space cooling load, the 2 control systems operate under dynamic conditions, and it have variable operation parameters. For the fan speed control system, its variable operation parameters mainly have the fan speed and duct static pressure. And for the valve control system, its variable operation parameters mainly include the mixing air temperature, the supply air flow rate, and the chilled water loop pressure differential here. Also, instead of the linear systems, these 2 control systems are nonlinear in nature, with its components having variable gain and time constant. For example, here, this figure shows the fan duct gain versus the fan speed. We can see that the fan gain, which is the ratio of the static pressure change over fan speed change, will increase as the fan speed decrease here. But the controller is designed as a design condition by assuming that the system has fixed gain, but actually the gain go this way, the fan gain go this way, and finally the system will respond fast and aggressive with increased gains as a partial load with lower fan speed. Similarly, for the valve control system coil gain, which is the ratio of supply air temperature difference change to valve position change will increase as the mixing air temperature decrease here. And if we design the controller at this condition and assuming that it's fixed, and actually under higher mixing air temperature, the gain will go this way, and also it will have a faster and a more aggressive response under higher mixing air temperature. So the current control issues under the dynamic operation conditions, and you have that, is that the system is designed as a single loop control system with fixed gain controllers designed for linear systems. But our control system are nonlinear with variable gain and time constant. Consequently, the system tends to be unstable at partial conditions with higher gains, and this will consume more energy and will also cause this equipment wear. Here, this is a supply air temperature in a gym. We can see that like over 10 days, the supply air temperature hunting all the time. Actually, we are doing another project, the same project, and the water loop pressure also like hunting all the time. So to better design the control system, we have to evaluate the control performance under variable operation conditions. Current performance evaluation approach mainly include experimental tests and the time domain simulation. For example, here, if we want to evaluate the control performance under variable mixing air temperature, then we have to do the time response simulation at each condition with different mixing air temperature. This type of approach is very time consuming and costly, and sometimes, especially for the test, is infeasible. So here comes to our motivation, how to evaluate the nonlinear control performance under variable operation conditions and identify the unstable conditions using a more efficient and effective approach. Based on this motivation, our project is to develop an operation parameter-based distribution technique to evaluate the nonlinear control performance without requiring time domain simulations. Luckily, we have the closed loop poles that can be used to evaluate the control performance without the time domain simulation. Here, take the fan speed control system as an example. This is a block diagram of the fan speed control. Here, if we increase the duct static pressure here, then there will be an error between its set point and the output pressure measured by the pressure sensor. The controller will convert the error to a VFD frequency command to increase the fan speed here, so that the duct static pressure can reach to the new set point. The closed loop transfer function, which the ratio of the control output to its input. We have this closed loop transfer function. We can see that once given the input, the output can be determined by the closed loop transfer function, and also the controller and the three components will all impact the denominator of the transfer function, closed loop transfer function. And the closed loop poles, which are the roots of the characteristic equation, can determine the control its performance. That is, the gain and time constant of each component, in addition to the controller, will determine the closed loop pole location, and the closed loop pole location can determine the control performance. Here, to evaluate the control performance, we have three performance specifications. The first, the peak time, is the time for the response to reach its maximum value for the first time, and the settling time is for the response to reach a within 2% of its final steady state value. And the overshoot is a ratio of the maximum value minus its final value over to its final value. In practice, the ideal control performance is that we want the response to get its set point faster and smoother. So we want shorter peak time and settling time. We also want a smaller overshoot. Here is the pole locations and the corresponding step, the step response here. If the poles have the same real parts with its imaginary part move upward, then its peak time will decrease. Here you can see the 0.3, the peak time is shorter, and the settling time remains the same here, and its overshoot will also increase at 0.3 here. And if the closed loop poles have the same imaginary part with its negative part, with its real part move to the left, and then the peak time will remain the same here, but settling time will decrease. Here we can say point to have shorter settling time, and it's also its overshoot will decrease here. And if the closed loop poles have the same angle and move to this direction, with its imaginary part move upward and the real part move to the left, then the peak time will decrease, the settling time will also decrease, while its overshoot remains the same. So because the control performance can be determined by closed loop pole locations, for the linear systems with fixed component gain and time constant, traditional Ruther-Locker's technique is developed and is applied to track closed loop poles paths in S-plane as controller gain is varied. And these Ruther-Lockers can give quantitative and quantitative information about performance without the time domain simulations. And we can mainly use it for design controller. Here, for example, this is the Ruther-Locker's O1 control system. As the controller gain increase, the pole location move from 0.1 to 0.2. We can see that compared to 0.1, 0.2, the imaginary part move upward, and the real part moves right to the right with large angle here. So 0.2, the time response for 0.2 should have the larger overshoot here, and the shorter peak time and longer settling time here. And specifically, if the closed loop pole move to the right half plane, the system will become unstable. Here is the unstable region. But for our control systems at air handle unit, they are nonlinear systems. Its operation parameters can impact its component gain and time constant, while it has fixed controller gains designed at design condition. So we propose an operation parameter-based distribution to check closed loop poles paths as operation parameters are varied. So here, take the fan speed control system as an example. This is the closed loop transfer function. With the variable operation parameters are fan speed and static pressure. Under each operation conditions, we can derive the component gain and time constant. With the component gain and time constant we can calculate the closed loop poles. And if we calculate the closed loop poles under each operation conditions, then and locate it on the finger, finally we can get our operation parameter-based distribution, which track the closed loop poles paths as operation parameters are varied. Let's do a quick comparison between the Ruther-Lockers and our proposed route distribution. The traditional Ruther-Lockers are for non-linear systems, with the system has linear components with fixed gain and time constants, and this controller has one variable gains. And for the finger, it will be the real and imaginary part in the S-plane, and it will be a two-dimensional finger. For our distribution, it's for nonlinear systems, and its components are nonlinear with variable gain and time constant with multiple variable operation parameters. And its controllers are designed as fixed gain at the design condition. And for its finger, it will include the real and imaginary parts with multiple variable operation parameters as independent inputs. For example, if we have two variable operation parameters, finally the root distribution will be a four-dimensional finger. Here is the full picture of our studied air handling unit in the University of Oklahoma, serving an educational building. Here, this is the outdoor air duct. The outdoor air and the return air here will mix as a mixing air chamber and will flow through the cooling coil and cooled by the chilled water through the cooling coil. And finally, it will be delivered by the VFD motor fan to the space to cool our space. During our test here, this is the block diagram, and this is the VFD when open. You can see that this is the VFD, and this is the supply air temperature sensor on the supply air duct. And this is the cooling coil valve and with an actuator. Then for the fan speed control system, we have to measure the fan speed. The fan speed can be obtained directly from the VFD, and we have to measure the duct static pressure using pressure sensor. We have to measure the supply air flow rate using a flow meter. The first step to sketch the root distribution is to determine the component gains and time constants. Generally, there are two methods. One is using the physical model by linearizing the nonlinear differential equations. Another one is a data-driven model by identifying through open-loop tests with step response. In my study, we use the data-driven model. And to identify the VFD motor and fan duct components, we conducted the open-loop test by overriding the VFD frequency at different values. Here, this finger, the left finger shows the VFD frequency command and the corresponding fan speed. Then with this response, we can calculate the VFD motor gain, which is the ratio of the fan speed change to the command change. Similarly, here, this finger shows the fan speed and the duct static pressure. With this data, we can calculate the fan duct gain, which is the ratio of the duct static pressure change to the fan speed change. And for the time constant, we have to measure the time for the amplitude to reach 63% of its final value. Here is the identification results. You can see that the VFD motor and sensor all have the fixed gain and time constant. And for the fan duct, it also has fixed time constant, while its gain varies with fan speed and duct static pressure. Here, we can say that the fan duct gain is not constant. We regress the fan duct gain at a function of fan speed and the duct static pressure. Here we get the expression. Up to now, we already finished the step 1 and step 2 to sketch the root distribution. Then we'll follow the procedure. The next step is to generate various operation conditions. To determine how many various operation conditions to generate, we have to analyze the fan duct gain sensitivity and the volatility. We calculate the derivation of the fan speed. It keeps it remains less than 0, and the direction of the fan the duct static pressure, it keeps larger than 0. That means the fan duct gain is monotonic. And as the fan speed increase, the fan duct gain will decrease. And as the duct static pressure increase, the fan duct gain will increase. So for our study, we generate 1080 by 80 various operation conditions. Here is the finger shows the fan duct gain on the various fan speed and duct static pressure. Here, because if we put all the parameters into one finger, it will be a 4-dimensional finger. To make it clear, we separate the real part and the imaginary part and use the contour line to show its value. We can see that as the fan speed decrease, the duct static pressure increase, the real part will go this way, with the negative real part will become smaller, and finally it will be larger than 0. Here, the yellow, orange, and green range all show the real part larger than 0. And similarly, the imaginary part will also go this way, will become larger. If we put the closed loop poles as the rule lockers, we can say that at the fan speed decrease, duct static pressure increase, actually, as planned, the closed loop pole will go this way, means that its response will become more aggressive. And finally, here for this yellow and orange region, with positive real parts, the system will become unstable. Here, this is unstable region here. So using this root distribution, the unstable region can be identified. Also, the worst conditions is under the higher duct static pressure with lower fan speed. This is the full picture of the root distribution here. And to validate the root distribution, we conducted experimental tests in the air handling unit introduced before. Here, there are 3 operation conditions marked on the root distribution. Here at condition 1, we have higher duct static pressure and higher fan speed. Then, to generate operation condition 2, we decrease the set point of the duct static pressure. And for condition 3, to generate lower fan speed, we two dampers are closed here. So here from the root distribution, point 1 should have the most aggressive response, also the same, we can say that. And at point 2 here, because it had the largest negative real part, here we'll have the most stable response also. At point 2, the response is more stable here, and the point 3 has the performance in between. We can see that our test results match the root control performance predicted by the root distribution. Here also, we also calculated some numerical index, the fan speed oscillation range, the duct static pressure oscillation range, and the mean square error of the duct static pressure. At point 1, it had much higher value than that at point 2. It has to be noted that the root distribution already considered the controller. So the controller will impact the root distribution. If we design the controller with larger controller gains, as a result, the contour line of the real part will move downward. It means that the system unstable region will becomes larger, and the operation condition at point 1 might be unstable. That means if the controller is designed improperly, and we will have more conditions on the unstable. Then we have the conclusion. The operation parameter-based distribution can effectively predict the nonlinear control performance at all possible operation conditions. It can identify the unstable ranging and identify the impact of varying operation parameters. Also, we can get the conclusion that more effective and practical control strategies are desired to handle the control issues caused by the nonlinear errors. This is the future work. And compared to the root lockers, the merits of the distribution is that it extends the conventional root locker technique with only one varying parameter to the distribution technique with multiple varying parameters. It can be applied to the control performance evaluation for nonlinear HVAC systems instead of just the controller design for linear systems. Also, the control performance can be evaluated without requiring time domain simulation or field tests. Thank you for attending. Thank you for listening.